Hi everyone, good morning, good afternoon, and good evening. Thank you all so much for joining us today for our fourth bootcamp session. My name is Stephanie Tropp. I'm a data scientist on the Cytobank team within Beckman Coulter Life Sciences, and I'm excited to talk to you today about using FlowSOM in Cytobank. Also joining me today from our home office is my teaching assistant, Pinball. As you can see, she's been really engaged for the first half of our Cytobank Pandemic Bootcamp series, and she's all geared up to dive into more advanced analysis techniques today. In the first 3 webinar sessions, we've gotten started with this recommended data analysis workflow to help you get the most out of your data. We already reviewed how to quality control and clean up your cytometry data, do any gating that is needed if you know you're interested in any specific populations, and beginning exploratory data analysis with viSNE. Today, we'll continue where we left off, starting with data that have been through dimensionality reduction. We'll take these data through the FlowSOM algorithm for clustering, and then return the resulting clusters back to viSNE for visualization. So starting with our viSNE map, we'll use FlowSOM to first identify what distinct populations or metaclusters exist in a sample. Then, we will look more in depth to understand the phenotype of each metacluster, and ultimately, use metaclusters to compare populations across samples. FlowSOM is one of many clustering tools that are being used to analyze cytometry data. The overall goal of these tools is to automatically and objectively identify cell populations and subpopulations. This is done by iteratively grouping together cells with similar marker expression. Clustering can be used to discover if there are populations that you're missing by gating them out with traditional hierarchical gating methods. By the time you complete comprehensive manual gating, what percentage of events did you assign to a population? How many did you exclude along the way? Maybe those cells are important. Clustering can help you to identify these events. Then, you can use the results to easily identify differences across samples or groups as well. Clustering tools used for single-cell data have largely been adapted from other fields, and they vary widely in design and performance. They can vary in whether the user has to input a cluster number, if and how downsampling is performed, how intensive the computational requirements are, how easy it is to access the tool, for instance, if you have to be able to program in the command line, and how interpretable the results are. As FlowSOM has emerged as a clear leader for many applications, we integrated it into the Cytobank platform. So here's just a very small sample of some other clustering algorithms used today in cytometry. They're described in this review published a few weeks ago. They all use different clustering methods and have different strengths and weaknesses. FlowSOM in particular uses a hybrid 2-stage approach to clustering, which gives it an advantage over other methods in speed. So FlowSOM has been a very popular clustering algorithm since it was published in 2015, and its primary objective is speed. It's very fast because of its 2-step clustering process. First, it clusters events using a self-organizing map, or SOM, which is where the name FlowSOM comes from. A self-organizing map is a type of artificial neural network using a grid of nodes that each represents a point in multidimensional space. It assigns cell events that are similar to each other, based on expression of selected markers, to the same node or neighboring nodes. The result is this n by n grid of nodes that correspond to cell clusters. After that, the center of each node is used to represent the node for further hierarchical consensus clustering, producing metaclusters, shown here in the shading. Hierarchical consensus clustering is slow when applied to individual cell events, but here it's only being performed on a limited number of clusters instead of individual cells. Generally, it is the metaclusters that are phenotyped and assigned names. These clusters can be visualized in a minimum spanning tree. The minimum spanning trees are incredibly informative, coming in 2 flavors: star charts that indicate the simultaneous expression of each marker per cluster, and pie charts that indicate the correspondence of each cluster with any manually gated populations. Another unique feature of FlowSOM is that these minimum spanning trees can be applied to new samples to compare between samples over time. In multiple benchmarking studies of clustering algorithms, FlowSOM has been shown to rank high in speed, precision, coherence, and stability. One potential drawback for some of FlowSOM is that it does not determine cluster number. However, it is well suited for many cytometry applications overall. Here's one of the intuitive visualizations generated by FlowSOM, the star chart. The star chart indicates for each cluster the mean marker expression of all markers you selected to plot. This allows you to simultaneously see the relative expression of all markers across clusters. For example, in the top group of clusters, there's maximum expression of the light and dark blue slices corresponding to CD4 and CD3, which is consistent with our expectation of CD4 T cells. The star charts can be used as a starting point for annotating the data. The second visualization, pie charts, show both the bird's eye view as well as the detailed view of your sample. From the ground up, we get to see how each cluster compares to manually gated populations as the pie slices. Doing any manual gating ahead of time is optional, but it is helpful to give confidence in your results and put them into the context of what you already know. To take a look at the top branch of clusters, the pies are lime green, turquoise, and blue, corresponding to different manually gated populations of CD4 positive T cells, and some CD3 positive T cells that didn't make it into one of the manual CD4 gates. Zooming out, each of the clusters is shaded with a color corresponding to its metacluster. Metaclusters are groups of clusters that look like each other, corresponding to the larger populations in the sample. And after assessing the comparisons to your manual gating and marker expression, the user can annotate or name these metaclusters. In addition to having great speed and impactful visualizations, FlowSOM is also powerful in allowing you to map new samples to a self-organizing map you generated on other samples. You can then compare cluster size and composition across samples, both visually and quantitatively, which is very beneficial for longitudinal studies. We'll now walk through how to set up a FlowSOM run in Cytobank, then how to interact with and download the results, given that the data have already been QC'd, gated, and viSNE has been run. We'll use a 20-color dataset of PBMCs that were acquired on a Cytoflex LX, first identifying and phenotyping the metaclusters, then comparing across 3 different donors. The panel is a pretty broad immune phenotyping panel, including markers to identify T cells, NK cells, B cells, monocytes, DCs, and granulocytes. Now imagine that already at this point, you're looking at this table and seeing where you might have placed markers differently than I have. Unless you're using a standard protocol and panel, we all approach manual phenotyping differently based on our own experience and knowledge. So here's the basic gating hierarchy that I assigned to this sample. You likely would have done something different, maybe a little different, maybe very different. You can see the events that were excluded from my gating hierarchy labeled as just live and CD45 positive on the viSNE map. Let's see how we can use FlowSOM to generate more reproducible, comprehensive results very quickly. So now we'll take a look in the Cytobank platform. So here's the experiment we'll be working on within my Cytobank account. You can see this is the result of a viSNE analysis. I'm here on the experiment summary page, where I can see basic information about the experiment, all the linked experiments to orient us to where we are, and all the illustrations and analyses that have been done. So you can see here that I've already done a number of FlowSOM analyses ahead of time. You see the name, which you can change here. There's a link to the settings that it was run with, and there's a link to download the results for any of these runs. But let's go ahead and start a new run. So we'll come up here to the top navigation bar, Advanced Analyses, FlowSOM Analysis, New Analysis. We'll give it a name, and this will open up our settings page. We can follow along with some of these instructions here. So the most important settings are up at the top to choose your population, FCS files, clustering channels, and event sampling. For more help on any of these settings along the way, you can click the little I button, which will open up our support page with details for each section on how to set up your run. So to choose the population, I want to start with the same population I used in my viSNE analysis, the live cells. Next, I'll choose which FCS files I want to include to be compared together in this FlowSOM run. I'll choose all of my samples. Next, choose which channels you want to be included for clustering. Here, since I'm laying on top of my viSNE map, I'll include all of the channels that I included in my viSNE analysis. Next, event sampling. You could choose equal, proportional, or to use all the events across your files. And you can look up here in your FCS files section to see how many events there are in total in your files and how many are in the population that you selected. In this case, because these files came from the result of a viSNE analysis on live cells, only live cells are in these files, and they're already equally sampled, so I can choose all events or equal or proportional, and they'll all give me actually the same result in this case. You can run up to 4 million events per run on Premium Cytobank and up to 8 million on Enterprise Cytobank, and so I'm well below that threshold here. Next, we'll get into the algorithm settings. First, we can choose whether to create a new self-organizing map or use an existing self-organizing map from another run. In a fresh experiment, you want to create a new self-organizing map, which we'll do here. If this experiment was part of a series of longitudinal experiments, or you wanted to compare this to a map that you already made, you would select the button for use an existing SOM from another run. And when you open the drop-down, you'll see all of your other FlowSOM experiments to where you want to pull your self-organizing map from. Next, you can choose which clustering method you want to use for the clustering of clusters into metaclustering, that second clustering step. It's strongly recommended that you'll get the best results with hierarchical consensus clustering, but you are welcome to compare to the other options as well. Next, we have to choose the number of metaclusters and the number of clusters. So the number of metaclusters should roughly correspond to the number of bigger populations that you expect to see in your sample. You can go on a few pieces of knowledge for a starting point to pick this number. First, if you have an idea of how many populations you expect to see in your sample, you can go with that number and maybe increase from there. If FlowSOM, it's recommended to over cluster and then merge clusters that look like each other if necessary. So option 1, go based on how many populations you expect. Option 2, take a look at your viSNE map, see how many distinct islands you have, and you could go based on that number and add a little bit higher from there. So whatever you choose, you are able to very quickly and easily set up multiple runs with multiple settings for your metaclusters and clusters and compare them to see where you think that optimal number is. So here for this run, I'll just start with the default of 10 metaclusters and 100 clusters. The number of clusters, this refers to the number of nodes in your self-organizing map, which is a grid, it's a square, so all the options here are squares. Next, the number of iterations. This is the number of times that the clustering is performed to arrive at the best result. The authors found that optimal results were found with 10 iterations, but you're welcome to increase that number if you wish. And then finally, optionally, you can set a random seed. If you don't choose one, Cytobank will choose one for you, and it will tell you that seed along with the results output. Next, how do we want to transform the data? You can choose, if you'd like, to check this normalized scale box, which will apply z-score normalization across all the selected clustering channels. This will put all of the channels on the same range. And this might be something that you want to try if you have a very different dynamic range across your channels, even though they might have similar biological importance. And then you have to choose which compensation matrix in Cytobank to apply to your data. Because you use the file internal compensation matrix in this experiment for gating, that option is automatically selected. And then finally, we have some settings to use for our PDF output results. These are all the plots of the minimum spanning trees that we'll get. We can choose the populations for the pie charts and which channels to plot in the minimum spanning trees. So for pie charts, I like to use up to a number of populations that I'll be able to easily visualize at once within a pie chart. So maybe that's 10 or 12, no more than that. And if you want to set up different runs to look at different populations, then you can just copy all your settings and select a different group in your next run. For this run, I'll try to stay with my bigger populations. And I'll leave on all the channels to plot so I can see the marker expression of all the channels in the minimum spanning trees. Cluster sizing. Do you want the size of the clusters on the minimum spanning trees and in the grids to reflect the relative abundance of that cluster, or do you want them to all be equal? The size can be informative, so I'll keep it on relative. If you have a very high cluster number, you might want to turn down the max relative cluster size so that the clusters don't overlap too much. Then you can choose to generate PDFs or PNGs or both, and you can choose on which output files you want to put on that shaded metacluster background in your plots. So those are all the settings. So let's hit run. Now for our first pass here, we used a very low number of metaclusters and clusters. Let's copy these settings and try again with more so that we can compare. So I just hit that copy settings button. I can give it a new name. Give it however informative a name that you want. I'll set up for 20 metaclusters and 400 clusters. I'll come down here and change those values, 20 metaclusters, 400 clusters, and run again. So you can see the status of the run that we just started up here, and the status will also appear within your experiment manager. So let those run for a couple minutes, and we'll go back to our presentation. Okay, so when we get our results, when they're done in a few minutes, the first thing that I want to do is take a look at the quality of the metaclusters within Cytobank in the resulting FlowSOM experiment. I want to determine if I set up the right number of metaclusters. So I like to start doing this by visualizing the metaclusters on top of the viSNE map to look for any concordance of the metaclusters and the islands. Take a look, see are there too many, are there too few, and repeat this with different settings, changing those numbers if needed. So this is a really tough question that FlowSOM doesn't automatically answer for you. How many clusters are there in your data? And there's a balance, right? If you choose few clusters, your data are a lot easier to interpret, but you're more likely to miss rare populations. And if you choose a high cluster number, it's harder to visualize, to understand easily what's going on. You might introduce some more noise into your results, but you have a better chance to find rare populations, and your metaclusters will be more pure, more homogeneous. So fortunately, within Cytobank, since you can set up so many runs, you can iteratively set up different cluster numbers. And as I mentioned, we recommend that you overcluster and merge if needed. So for these data, here's what changing the number of metaclusters and clusters look like. So at the top left is a viSNE map overlaid with my manually gated populations, followed up by FlowSOM results. Each plot shows an increasing number of metaclusters and clusters from 10 to 22. You can see that the concordance between the viSNE islands and the colors start to improve around metacluster 18, leaving us to focus on 18 or more metaclusters. And if we consider the panel used here, there were markers for every major lineage found in the peripheral blood, so we do expect to be able to identify a large number of populations. And with this workflow, you can check your results visually to make sure they're logical to you and consistent with your prior knowledge, and that you're not just blindly trusting the algorithm. So I chose to focus here on the result from the run with 22 metaclusters to walk through how to phenotype them. As you can see, with the highest number of metaclusters I ran, 22, it's a little more difficult to look for patterns with this large number of metaclusters, but each metacluster will be fairly pure. So in Cytobank, your FlowSOM result would create a new experiment to interact with in order to phenotype the metaclusters, optimize the metacluster number, do your statistical analyses, and so on. Here's an example of using a heat map to assess the cluster identities by median marker expression on the left and the histograms on the right. Each row is one of 22 metaclusters, and the columns are all the markers included in the FlowSOM run. This can be all set up within the working illustration of Cytobank. If you've done any manual gating, you can use those gates as a starting point for interpreting the metaclusters. On the left are the manual gates I made overlaid, and on the right, the metaclusters. You can see how much clearer the islands are when overlaid with the metaclusters than with the manual gates. So you can use this strategy to assess correspondence of the metaclusters with the viSNE islands and with your manual gating. We can see pretty good correspondence between major populations in particular. For example, here we can see that the CD19 positive B cell population on the top viSNE clearly overlaps with FlowSOM metacluster 15. To verify that metacluster 15 is indeed B cells, we can look at the expression of markers that we know to be important in defining B cells. These plots shown here can all be generated within the Cytobank working illustration. And you can use the gating page to rename any metaclusters as you phenotype them. If you're doing discovery, you're probably interested in populations that perhaps don't align with manually gated populations. For example, on the top, there was a large population that I didn't gate as anything more specific than CD45 positive, that orange population. We can see that metacluster 3 on the bottom is in the same position. When we try to identify this metacluster by looking at the expression of all the markers and return to a biaxial plot strategy as well, we can see that metacluster 3 is CD15 positive and side scatter high, so we can incorporate our prior knowledge to identify them as eosinophils. Let's check back with our FlowSOM run in Cytobank, see if it's done. So this is left to the result page for that second run that I set up. Let's take a look at the first run. So here is another window showing all of the FlowSOM runs. We see that the first one I set up was done and the second one is running. So we'll take a look at that first one. The default working illustration will automatically bring us to a page where the metaclusters are overlaid on the viSNE map. We can click on this link up here for the FlowSOM settings. And this is where all of our settings are stored that we can refer back to at any time. We can download these as well. When we download this run info and plots, it will give us a document with these settings, as well as all of our results, different tables of data and PDFs of our minimum spanning trees and grids. So let's check on our second run as well. And now that one is completed too. So I'll open that up and we can compare. Okay. So on the left here is my 10 metacluster result, and on the right is the 20 metacluster result. And you can see that increasing this number of metaclusters looked more beneficial in assigning different metaclusters to each of our separate viSNE islands. Perhaps we could go up from here a little higher as well, as these two distinct islands are the same color. We can download the results for this run as well if we wanted to. Okay. So each of these analyses are now in their own experiment, their own FlowSOM experiment. If we want to go back to look at our tree of linked experiments, we'll see exactly where we are in our analysis. So this FlowSOM run is a child experiment of the viSNE run called Live Single Cells, which is a child of our original parent experiment. All right, so let's take a look at some of these result files and see what we can learn from them. So with your downloaded results, here are some of the files that you can get and the most important ones to focus on. So within this channel colored MST folder, you'll have files for each of your individual samples, as well as one that represents the aggregate. These will be trees that are colored by the individual expression of each marker that was selected to plot. Down here, the population pie charts. Those will be the minimum spanning trees with the pie charts that correspond to the manually gated populations. And the star plots are the minimum spanning trees where each cluster has the pie slices that correspond to mean marker expression. So how can we use these results to now compare the three different files in our sample? We can do this quantitatively with some of the tables that you can download. In particular, if we want to compare abundance of populations, we can compare the abundances of the clusters with cluster abundances, or the metaclusters with the metacluster abundances files. So these will be spreadsheets that look like this, and you can import them into any of your favorite statistical packages for statistical testing. You can also compare abundance by looking at event counts within Cytobank, within the working illustration. So especially if you've used equal sampling, if you select event counts, you can directly compare from sample to sample. So here we're looking at a heat map and the course of the corresponding event counts for each of the three samples in this experiment of each metacluster. If we want to compare where they differ, we can take a look at this heat map or the numbers and see where we might want to explore to see differences between samples. So here's how we could do that visually with the downloaded population pie chart minimum spanning trees. Across samples, from sample 1 to sample 2 to sample 3, we can see how there's differences in cluster abundance as reflected by the size of the pies, as well as composition of the pies that correspond to the different manually gated populations. So we can do this visually right here. There's some differences that can jump out at us right away. For example, sample 2 has much smaller pies in this top metacluster. It has much smaller pies in the metacluster right below it, and a lot larger pies in this middle section here. Your eyes can probably see some other differences as well. So this is how we compare them visually. Quantitatively, we can go back and take a look at the metacluster or cluster abundance files that we exported as well. So in this example, I chose my 22 metacluster result, and there's a lot of overlap. It can be kind of hard to identify exactly which metacluster corresponds to which section of the tree. So the results also come with a legend file that shows you the position of every metacluster on your minimum spanning tree. So you can refer back to here and identify which metacluster you're looking at. So if we wanted to use our heat map here where we see the abundance for each metacluster and see where those metaclusters that look interesting are on our map, we can refer back to this legend. So for example, from our heat map, we see there's differences in metacluster 3 and metacluster 5. and we can see where to locate those on our population pie charts. So here's the position of metacluster 3 and metacluster 5, and those are indeed metaclusters that we could see differences in just by eye, but we also see those differences when we look at event counts. So here's how you can compare population to population visually by using your minimum spanning tree and quantitatively using the downloaded metacluster abundances and the event counts. So those are just a couple highlights of how to use FlowSOM in Cytobank. And as you work with it more, you can find more utility, more applications. So I hope we've shown you today how with FlowSOM, you can automatically and objectively identify all the cell populations and subpopulations within and across samples, as well as populations that might be missed by manual gating. The advantage of using FlowSOM in the cloud with Cytobank is that you can iteratively set changes, including different cluster numbers and metacluster numbers, to arrive at your optimal analysis. And with FlowSOM, your results can be reproducible because you're not relying on subjective or manual gating. However, you can use these manual gates to compare for validation against known populations. You can reuse self-organizing map across runs to be able to compare samples run to run. And all of your settings and results are stored within your experiment and will be available for download. I'll wrap up by directing you to some resources to help you with your analysis, whether you're already using Cytobank or not. If you don't have a Cytobank account, you can visit premium.cytobank.org to sign up for a free trial. You can find educational materials in our webinars and on the Cytobank blog. From our support site at support.cytobank.org, you can read plenty of comprehensive support documentation and submit tickets for technical support, as well as inquire about any account or training-related questions you might have. And finally, I want to let you know that we have a scientific services team that I participate in if you need help with a large or tricky analysis project. And with that, thank you again for joining us, and we're happy to take your questions.
Excellent work. Thank you, Steph, and thank you all. We've gotten a lot of really good questions from you guys. So what we're going to do here is I'm going to try to go through all of them. And as I said previously, what we don't get to, we will get back to you via email. And one more note, again, if you are asking your questions anonymously, we will not be able to get back to you via email. So first and foremost, I'm just going to introduce our panelists who have made these seminars happen. And there are fabulous Cytobank support groups. And first of all, we have Steph, whom you've just heard talk and give you the presentation on FlowSOM. She's our data scientist. We have an additional data scientist, Jihao, who's also joined us on the panel today. Chinjin is on the line as well. She's our application scientist for Cytobank, and Sarah Shuett, who is our technical sales specialist for the East Coast. So all together, we're going to try to answer all of your questions. And of course, my name is Alina, and I haven't actually introduced myself in the beginning, so I apologize for that. I'm the field marketing manager for Beckman Coulter. Okay, so without further ado, the very first question. How do you utilize FMOs in the dimensionality reduction clustering algorithms, which is actually a really important question. So would you import the FMOs into your actual analysis, or would you use them to do your cleanup of data? And I'm going to refer this question to Chihao.
Hey, Alina, thanks so much for the question. Yeah, that's a great question. And my recommendation is that you you don't want to run your FMO samples with FlowSOM. You should only run the regular sample data with your FlowSOM, and then after you get your metaclusters, you can and then you need to assign cell type for those metaclusters. That is the time when you should look at your FMO samples to decide what is the right cutoff to define the boundary between the negative population and positive population for each channel, and then you can base on that information to gate and to annotate your metaclusters. I think that would be the right way to do that. And potentially, if you want to do some kind of a QC, simple QCs, you might be able to run your FMO samples with FlowSOM. But in that cases, you should be able to get very like distinguished metaclusters, but again, this is just a like, and another possible way to use it is that you can use your FMO samples to build a self-organizing map model, like what Steph mentioned in her talk, and then you can try to apply that model to the rest of the regular samples. But again, if there is a huge batch effect between your FMO samples and regular samples, this method would not work very well. I guess overall, I would recommend you just use the FMO samples to determine the cutoff values for the positive populations, and don't use it to run FlowSOM.
Okay, excellent. Thank you so much, Yao. Another question that we have that's actually a really good question, and I'm going to get Chinjun to answer this. Hello, Zoya, and she asked, what are the advantages of FlowSOM over SPADE? When would one application be used versus the other? Chinjun? Oh.
Sounds like maybe.
Yeah, maybe she.
Go ahead, Shihab.
So maybe you can hear me now.
Yes, we got you.
Sorry about that. Yeah, so it's a great question that we have been asked about this quite a lot. So FlowSOM and SPADE are both clustering algorithms. In most of the cases, they can generate comparable results because FlowSOM using the sum for the self-organizing map. As a matter of fact, it can take more events and it's run much faster, as Steph mentioned in her presentation. And there are some other differences versus like visualization, right? So both SPADE and FlowSOM use minimum spanning tree for visualization. However, FlowSOM has a lot more visualization, like the pie chart, the grade. Now, also, FlowSOM has a second clustering step, the metacluster step, that SPADE doesn't have. However, SPADE has the interactive minimum spanning tree where you can highlight channels one at a time, and you can do bubbling. So it's a different process of visualize your data. There are some debate about, maybe SPADE is a little bit better at identify rare population. It's debatable, but some people believe, they want to use SPADE for those studies. However, if you are working on longitudinal studies, I would definitely recommend using FlowSOM, as we can always reuse the SOM to get a comparable results across different samples and different runs. Hope that's helpful.
Thank you so much. That's perfect. Okay, a very technical question that maybe someone skipped, but what does the cluster number refer to? So I'm going to get Steph to answer this.
So sorry. So the cluster number is the number of groups of events that you have selected for your data to be divided into. So let me go back to show you the grid. Okay, for instance, there we go. Here is a minimum spanning tree, and each of these circles, they're pie charts in this case, are a node or a cluster. So each of those represent a group of cells in this sample that look like each other based on selected marker expression. So the cluster number is how many of those you tell the algorithm to divide your data into. And with FlowSOM, it's built upon this grid right here, which means that this number has to be a square. And this is a setting that you set in your run from a drop-down menu of available options from 100 to 400 in Cytobank.
Perfect. Thank you, Steph. Okay. Another question. How does FlowSOM compare or work with Xshift? And I will refer this question to Chihao.
Yeah, thanks, Alina. So actually, again, like there are so many like different clustering algorithms available right now, and like among like besides FlowSOM and Xshift, like some of the people are also like phenographic. And according to like a paper published in like December last year, I think they report that like phenographic and Xshift like will behave will outperform like FlowSOM when detecting rare cell populations. But again, the performance of phenographic Xshift are impacted by the increased sample size. So if you have like large samples, and you probably can get more robust results. But on the other side, FlowSOM actually is relatively stable as the sample size increase. So if you run FlowSOM, you don't need to worry about, like, for example, you have clinical samples, like you only collect maybe like 500,000 cells from this patient, and you cannot like just go back to collect more cells. In that cases, you probably like FlowSOM is better option than Xshift and the phenographic. But again, and the other big advantage of FlowSOM is it is super fast, especially when you need to analyzing like huge data set. I'm talking like maybe you have like 20 million cell events in one of the group. And in those cases, I think FlowSOM, like you can get FlowSOM result within maybe a day or two, but you might not be able to get like results from, like, for example, like SPADE. SPADE will probably run maybe a week or something to generate the result.
Perfect. Thank you so much. All right, and another question, I'm just going to answer this one a little bit quickly because Steph has gone over it. Giovanni asked the question, if we do a time point analysis, so a longitudinal study, would the samples be equally sampled through viSNE so that you can track the changes in the metaclusters, i.e. changes in frequencies, expansion, and contraction? And the answer to that is yes. You would run them at the same time, and then you would apply the same SOMs on the actual samples. And if any of you have additional information, as in Steph, just correct me, or have I answered the question? Okay. All right. Would you explain how metaclusters can be annotated for certain cell types, such as T cells and NK cells? And Steph, can you answer this, please?
Sure. So in order to annotate the metaclusters, you have to rely on other knowledge that you have, whether you have already done manual gates, you can use those to compare to, or you can take a look at the marker expression if you haven't done those gates. So I'll just go into the app, for example, to show how we can do this. So here's one of the results that I just generated. And say that we wanted to figure out what this metacluster over here is. We'll use that one because that's the one I showed you, so I know what it is without pulling up all of the different markers at once. So we see this is metacluster number 3. So either you can take a look at all of the metaclusters and all of the channels at once. That's a little overwhelming, and you have a lot of metaclusters and a lot of channels. I'll show you what that looks like. You can do this with histograms or heat maps. So I selected all of the channels I want to look at, all of the metaclusters, and I'll just select one of my 3 samples for now. I'll make histograms, I'll overlay them, and then down here, I'll make my curve smooth and just select which channels to plot. We went over the illustration 2 bootcamp sessions ago, so I'm going a little bit quickly through this. I'll make this a little bit smaller. So to phenotype your metaclusters, you could start with something like this, where you're looking at all of your metaclusters and the marker expression. that's a little bit overwhelming, right? So if you want to focus on specific metaclusters and then narrow it down to specific markers that you know will be more helpful to you, then you can pare down from here. So for instance, if we want to look at metacluster 3, I think that was the one that I said was all the way on the right there that I already knew what it was. We'll take metacluster 3, and I like to compare that to everything else, to the ungated. So I'll just select those two. Anytime you make changes here, you click this update illustration button, and then it will load up all your plots pretty quickly. So now I'm looking at my metacluster 3 overlaid with the rest of the cells, and I can see the relative expression of each marker. So I can see right here that metacluster 3 is CD19 positive, it's HLA-DR positive, and I can scroll through, it's CD3 negative. So to me, I know that that is a B cell. If you don't know, you can use lots of resources like charts of CD marker expression. Ask your colleagues, because we don't know what each of these populations is made up of. And then I can go into the gating page if I wanted to rename that metacluster so it's easier for me to continue with my analysis. And I would do that by selecting that metacluster and then renaming it. And now that name B cells will appear in my illustration. So I hope that that answered the question of how to phenotype the metaclusters.
Yeah, I can also comment on that. Other than the methods Steph just mentioned here, another way to check on the metacluster expression is by looking at the downloaded results, the minimum spanning tree, where you have the channel, the tree colored by each channel. So that's another way you can go through all the clusters and the channel expression in the downloaded results.
Thank you, and I'll pull those up while we start the next question for you if you'd like.
Perfect, thank you. Okay, our next question is a pretty simple one. And I'm just gonna, if you're running a TISNE and then a FlowSOM, will you run FlowSOM on raw data or on the TISNE data? Will you include the TISNE 1 and 2 into your FlowSOM run? And I'm just gonna get Chinjin to answer this.
Yeah, definitely. So for analyzing the FlowSOM on top of viSNE, so you'll run on the viSNE generated results. So the viSNE experiment, after the viSNE run, that will have the viSNE channel in there. However, when you run FlowSOM on the FCS file, you will not necessarily run on the TSNE channel. Instead, you will still be running on the marker channels, but the file that contains the TSNE, so that after the FlowSOM run, you will be able to overlay or compare your metacluster or cluster on the viSNE map. But we would not recommend you run directly on the TSNE channel. So you still run on the raw channel, and you can visualize those results on the TSNE channel. That would be the workflow we recommend.
Perfect. Okay. So another question. So does the data you analyze in FlowSOM, is it already, oh, sorry, no, 1 second. Okay. I think the question is something like, can you analyze FlowSOM data that's already been analyzed by other software? So from previous cluster results. So can you input an actual FlowSOM result, a previous clustering result into FlowSOM and then analyze it additionally? And Jihao, can you answer this, please?
Yeah, sure. And actually, I just curious, like why you might want to do that, because like all the purpose of the clustering algorithm is to kind of help you reduce the dimension of your data. Like for example, you have like maybe like 20 marker data, and then you have to like group events based on the expressions of 10 markers simultaneously. And if you want to do this manually, it is challenging, and you might miss some very important distinguished cell clusters, and that's why like people will like run clustering algorithms such as like FlowSOM to kind of reduce the dimension of your data, kind of project all your events to a 2D plot, so that you can easily like identify the cell type for those like cell clusters. And if you already do that kind of analysis using other algorithms, and you definitely don't want to including those informations into your FlowSOM run, because it is, and I guess it is possible again, like, but for like unless you are an advanced user, you really understand like how does the FlowSOM algorithm work, you can do that. You might need to like specify a weight for those clustering algorithms produced by the other algorithms. You can incorporate, like you kind of you can run FlowSOM in the semi unsupervised approach, but usually we recommend you just like run FlowSOM using the like purely unsupervised approach to do the analysis.
Okay, thank you, Jihao, very much. Okay, does the integrity of the clustering depend on the number of events ran and or iteration, like within the TISNE run? Steph, can you answer this, please?
Okay, so the question is the integrity of the FlowSOM clusters on the number of events and the TISNE iterations, is that right?
Yeah, so basically, does the integrity of the clustering depend on the number of events ran or the iterations?
Okay, got it. I see. Thank you. So the number of events. So the impact of the number of events on the algorithm, the clustering outcome, is measured as something called stability. So based on how many events you run, if you run a lot or a little, do you get basically the same results? Does that number impact it? And FlowSOM is very stable to changing this event count. So number one, and number two, the TISNE we're just using for visualization. So the actual TISNE 1 and TISNE 2 values, as we talked about in an earlier question, we don't recommend putting those into the FlowSOM clustering. We're just visualizing on top of it. So if your viSNE map was run with a low or high iteration number, that's not going to impact any of the clustering results. It will just change the look of the visualization, how the metaclusters are overlaid on the viSNE map.
Perfect. Thank you very much. Okay, I had another really good question. Sorry. Okay, so this question is, when should one choose equal proportional or use all cells in the sampling? And then a related question from that is, does selecting unequal events from different FCS files create biasing in the MSD? Steph, did you want to tackle this one as well?
Sure, yeah. Yeah, so great question. So if you want equal weight of all your samples in the clustering, then yes, you want to choose equal sampling. I generally advise equal sampling. The only time I really would use proportional is if you have a sample or some samples that have very low event counts, because that will limit the number of events that you could take total from all of the rest of your samples as well. So you can run a lot of events in FlowSOM. You can run up to 4 million, as I mentioned, if you're on premium, and 8 million if you are on enterprise server. So the first option is if I have roughly equal amounts of events in my files, I just choose all events. If I have too many, I need to downsample, and I'll choose equal. And then proportional if I don't want to be limited by a sample with a small number of events.
Perfect. Thank you so much. Hopefully this is a simple question. How can I extract statistics from viSNE or FlowSOM? And Junjun, do you mind answering this one?
Definitely. So for the results, as for the FlowSOM, I would do the FlowSOM first. So for FlowSOM, the downloaded folder that contains all your cluster and metacluster abundance and MFI. So you then can definitely get those results directly from the download results, or further, you can do a lot of statistic export from the FlowSOM experiments. And in regard to viSNE, for the statistical export, if you gate it on the viSNE population or islands, you can also do statistical export normally as would with any other population that you manually generated. So there's a lot of ways to do the export, and if you go to our support site, you will get all those informations already to us.
Perfect, thank you so much. Can we merge clusters? Steph?
Yeah, so I'll go through and show that. That's a great question because it is a strategy that we recommend to do if you see that clusters or metaclusters really look like each other. So
can I follow up on that? So instead of merging clusters, when would you say, like if you know that the clusters are similar, would you not run a different iteration of the FlowSOM, or would you try to merge them? What would be, when would you choose one over the other?
Yeah, that's a good question. So if you see that you have multiple metaclusters that look like each other, so you think you've got too many metaclusters, and if you try to decrease your metacluster number, the algorithm might not make the same decision that you would. So if you want to incorporate your prior knowledge, which can be really useful, then I would merge them. And this is how we would do that here from the gating page. So let me just, as an example, say that I know that metacluster 1 and metacluster 2 are the same, which I don't know that, but we'll use that as an example. So we'll use, just to save time, this automatic cluster gates tool. Click there. Select a channel that contains the cluster IDs. Which channel do we want to use to generate clusters, to generate our merged clusters? I'll merge metaclusters. So I choose that channel. You don't have to give it a name. And I will put in parentheses here the numbers of the metacluster IDs that I want to combine like that. And then this will make a new population combining these two. I just have to refresh the page with that, which that message just told me. And then I'll have a new population. And I can rename that whatever I had phenotyped there. So it'll show up there, and I'll have a new population corresponding to those two. So that's how you would go through and merge. And it's much easier to do this, on your metaclusters, which all contain distinct groups of events, versus doing this with manual gating.
Perfect. Thank you so much. Okay, I'm going to take one last question, which has to do with metaclusters, and this is also pertains back to what we just talked about. How do we know if increasing metaclusters or the clusters improves the FlowSOM? And I'm also, is it okay if, Steph, would you like to take this one, or Chinjun, either one of you two?
Sure. Yeah, so improves, that's a great question. That's a subjective word, right? Depends on. Yeah. So what is your gold standard? What are you comparing to? If you trust that you had a really well-run viSNE map, then maybe you want to get your metaclusters to overlay on your viSNE map. If you trust your manual gating as the gold standard, which is how most clustering tools are designed and validated against, then you would want to look at your population pie charts and look for the concordance between your clusters and the pie charts. And then furthermore, that the metaclusters all encompass clusters with the same pies. So if Chenjun or Chiha want to add on to that, please feel free.
I think they're happy with your answer.
Yes, I think that's great, yeah.
Okay, thank you so much. So guys, we've run out of time, and we don't want to keep you for any longer. We want to thank you again, all of us together at Cytobank. We want to thank you for attending the seminar series. This is the 4th one. Please stay tuned, because we will reconvene our 5th session, which will happen next week on Tuesday. Until then, stay healthy and safe, and thank you for joining us, and have a wonderful weekend. Bye, everybody.
Thank you, everybody. Thanks so much.